Hi, everybody. Welcome to the Physical Property of Matters notes. We're focusing on volume, mass, and density, really focusing on that density part. Well, first question I have for you is what is mass and what is size? I know that seems like a crazy question, but mass is the amount of matter in an object. Okay. And when we think of size, what do we think of? Some people will say something that's big, something that's small. Okay. But in essence, when we talk about size, we have to basically think of volume. Okay, that's what we're thinking of. We're thinking of the word volume. So, real quick, I want to ask you a real quick question. Large objects always have more mass than small objects. True or false? Well, the answer is false. Okay, because you need to give yourself an example. Like, can we think of a large object or a small object that has more mass than a large object? Sure. What about a really kind of heavy, small metal ball and then like a large piece of paper? That small ball, even though it's smaller, it's going to have more mass. All right. What about objects made of steel and concrete always have more mass than objects made of plastic and styrofoam? True or false? What do you think? Objects made of steel or concrete always have more mass than objects made of plastic or styrofoam. Well, that's false again. Okay. What if I had a small piece of concrete, maybe the size of a baseball, still going to have some mass, but then versus, let's say, a school size piece of styrofoam. What about a school size piece of styrofoam? I always misspell styrofoam. I don't know why. It's right in front of me. I just doesn't seem like a word I want to spell. So if I dropped a school-sized piece of styrofoam on you, it would kill you. If I dropped this little baseball-sized piece of concrete, it would hurt, but it wouldn't kill you. All right. So again, remember, volume is the amount of measurable space. That's super important. Now, one that I need you to make sure you know is on a regular rectangle, that's length times width times height. Okay. You got to know that. But the other formulas will be given to you in this class. But basically, all volume is length times width times height. Okay. Take a second, pause the video. I want you to look up here. We haven't even talked about density or anything. And you tell me which one of these boxes above has the greatest mass, the greatest volume, and the greatest density. Go ahead and do that right now. All right. Well, which one has the greatest mass? Well, that's B. And why? Because it has more of these dots. These dots actually represent the matter or the particles or the atoms. I like to think of them as cookies. How many cookies are in each box? Well, B has more cookies, so it must have more mass. All right. What about volume? Well, volume is also B because it has a larger box. If mom said, hey, go in the other room and grab me the large box, you would grab box B. And now we get to density, something we really haven't talked about yet. But the density is actually equal here. How is it equal, you may ask? Well, you get to think about it. Look at the arrangement. Look at the matter spread out. If I drew a line right here, these two boxes would look exactly the same. So what if I stacked another box up? Well, it would look the same as here. Okay, so forth and so on. We'll talk about that here in a second. Density, by its definition, is density is mass per unit volume or mass divided by volume, where mass is measured in grams and volume is measured in milliliters. If you actually look at the math of the steel cube, you'll see because the volume is smaller, but its mass is larger, the ratio still gives the density of steel as 7.8. Unlike a nail, which actually has a larger volume, and its mass is actually a little bit bigger, when you do that math, you still get 7.8. One thing we need to understand is this as well. Some people always get this confused. 1 milliliter. So if I had a graduated cylinder with 1 milliliter of water in it, if I poured that 1 milliliter into an imaginary box to fill up the imaginary box, that 1 milliliter of water would fill a box that is 1 centimeter by 1 centimeter by 1 centimeter. So 1 milliliter of water is equal to 1 centimeter cubed. Again, here's a breakdown of it. Some people love to use the magical triangle. I don't tend to do my answer keys in that way, but This right here is where we got to live, right up in here. All right. But each one of those is for you. And if you see that, density is mass per unit volume up there. So Archimedes, there's a big old story about Archimedes. In class, I'll tell you about it, and we'll go through that. But I'm going to let this video kind of tell the true story of Archimedes. Here we go.
When you think of Archimedes' eureka moment, you probably think of this. As it turns out, it may have been more like this. In the 3rd century BC, Hieron, king of the Sicilian city of Syracuse, chose Archimedes to supervise an engineering project of unprecedented scale. Hieron commissioned a sailing vessel 50 times bigger than a standard ancient warship. Named the Syracusia after his city, Hieron wanted to construct the largest ship ever, which was destined to be given as a present for Egypt's ruler, Ptolemy. But could a boat the size of a palace possibly float? In Archimedes' day, no one had attempted anything like this. It was like asking, can a mountain fly? King Hieron had a lot riding on that question. Hundreds of workmen were to labor for years on constructing the Syracusia out of beams of pine and fir from Mount Etna, ropes from hemp grown in Spain, and pitch from France. The top deck, on which 8 watchtowers were to stand, was to be supported not by columns, but by vast wooden images of Atlas, holding the world on his shoulders. On the ship's bow, a massive catapult would be able to fire 180-pound stone missiles. For the enjoyment of its passengers, the ship was to feature a flower-lined promenade, a sheltered swimming pool, and bathhouse with heated water, a library filled with books and statues, a temple to the goddess Aphrodite, and a gymnasium. And just to make things more difficult for Archimedes, Hieron intended to pack the vessel full of cargo. 400 tons of grain, 10,000 jars of pickled fish, 74 tons of drinking water, and 600 tons of wool. It would have carried well over 1,000 people on board, including 600 soldiers. And it housed 20 horses in separate stalls. To build something of this scale only for that to sink on its maiden voyage, well, let's just say that failure wouldn't have been a pleasant option for Archimedes. So he took on the problem. Will it sink? Perhaps he was sitting in the bathhouse one day, wondering how a heavy bathtub can float, when inspiration came to him. An object partially immersed in a fluid is buoyed up by a force equal to the weight of the fluid displaced by the object. In other words, if a 2,000-ton Syracusia displaced exactly 2,000 tons of water, it would just barely float. If it displaced 4,000 tons of water, it would float with no problem. Of course, if it only displaced 1,000 tons of water, well, Hieron wouldn't be too happy. This is the law of buoyancy, and engineers still call it Archimedes' principle. It explains why a steel supertanker can float as easily as a wooden rowboat or a bathtub. If the weight of water displaced by the vessel below the keel is equivalent to the vessel's weight, whatever is above the keel will remain afloat above the waterline. This sounds a lot like another story involving Archimedes and a bathtub, and it's possible that's because they're actually the same story, twisted by the vagaries of history. The classical story of Archimedes' Eureka and subsequent streak through the streets centers around a crown, or corona in Latin. At the core of the Syracusia story is a keel, or corone in Greek. Could one have been mixed up for the other? We may never know. On the day the Syracusia arrived in Egypt on its first and only voyage, we can only imagine how residents of Alexandria thronged the harbor to marvel at the arrival of this majestic floating castle. This extraordinary vessel was the Titanic of the ancient world. Except without the sinking, thanks to our pal Archimedes.
So Archimedes, pretty amazingly brilliant man. Okay. What is going on here? Sorry about that. All right, back at it. All right, sorry about that. Okay, so again, his water displacement method. Okay, basically, we talked about this in class already, but we look at the bottom. But basically, we take our starting value, which would be 30 milliliters, its new value is 40 milliliters after the object's been put in. This is what we call our initial. This is what we call our final. So what we do is we take our final value minus our initial, and we get what the actual volume or our new volume is. So that would be 40 minus 30 would equal 10 milliliters. That 10 milliliters is the volume of that object without doing any measurement. Again, we need to remember that the volume or the density of water is 1 gram per milliliter. Okay, that's why in class, why does the oil float? We don't know the density of the oil, but we know that the oil's density is less than 1. Anything greater than 1 would sink. So again, just by looking at this density column, you should be able to say that the bolt has the greatest density, the ping pong ball has the lightest density, the dish soap would be in the middle, and we could even say that the cherry tomato that's floating in the dish soap has exactly the same density as the dish soap. Okay. Why does this giant aircraft carrier not sink? Well, that has to do with the video about water displacement. But if we displace enough water, that makes our density lighter than 1. We will always float on water. All right. You're going to need to click on these 2 links in the actual notes in the link above this in Schoology and watch the boat float and then the Mythbusters talking about why the boat floats. Okay. Real quick, on your notes and everything right now, which one of these has the greatest mass, volume, and density? Right now, pause the video and take a guess. And I guess I should have said, this is box A and this is box B. That would help you out greatly. Which one is the greatest mass? Well, box A is. It has more cookies or more balloons or whatever you want to say. Which one has the greater volume? Well, we're only looking at the size of the box. The boxes are the same size. So actually, lied, the volumes are equal. Which one has the greatest density? Think of population density. If these were rooms, which room would have more densely populated people? Well, that would be A. All right, last one, and we're done. Again, which one of these have the greatest mass, volume, and density? Take a few seconds. This one's box A. This one's box B. Take a guess and go. Hopefully you took a guess. Here we go. Which one has the greater mass? Well, how many cookies are in this one? 1, 2? 1, 2. Ooh, their masses are actually equal. Which one has a greater volume or more measurable space? Mom asked you to go get the bigger box. Which one would you go get? You would say B. And then which one has the greatest density? Think about it. The rooms are different sizes now. So if you had to live with another person, would you want a big house or would you want a small house? Where are you going to feel more densely packed? That would be A. All right, we're going to do a lot more practice on this. Don't worry. Everything's going to be fine. But if you have questions, make sure you ask. Again, Mr. Tima, out.